Okay, so the new concepts, we're going to learn how to solve some rational equations, even though in the past, if you have taken other pre-calculus classes, you would have done some rational equations. We're going to do transformations. We're going to do rational functions in standard form because we need it for transformations. Domain of rational functions, because now we're going to look at ratios that have x's both in the top and the bottom of a fraction, meaning we have to put the exclusions. What can we not have in the denominator of those expressions? And then we're going to look at some particularities of the equations of the functions that we call rational functions, so we can deduct some parts of the graphs of these functions the same way we have done for polynomial functions. Okay, so their equations will give us clues on the graphs. I think I printed your notes just one-sided, right? So that was just my bad. So it's not as thick as it feels, okay, in case you're wondering. So the first lesson is going to be some review of rational expressions, and then towards the end, we're going to do some equations. Rational expressions has the form P of x over Q of x, where P of x and Q of x are polynomial expressions, with the condition that the Q of x, the denominator polynomial, cannot be 0. So some examples is 1 over x, 3 over x squared, or let's put some x in the numerator as well, x over x plus 1, so linear over linear, or quadratic over quadratic. Let's do that, x squared plus x minus 1 over x squared plus the 2 or 3x minus 2. I'm just kind of inventing them on the go. Just so you can see the pattern, you just want to have polynomial over polynomial. Notice how in the numerator, we can definitely have just a number as well. That's still going to be called the rational functions. The idea of rational functions mostly focuses on the denominator, the bottom expression. Okay, so now these rational expressions, because of this condition, the denominator cannot be 0, they will have something that we call non-permissible values. In short, NPVs, because non-permissible values is a mouthful, right? So NPVs in short. Non-permissible values will be later on into our function, they will become domain restrictions. They are any values of the variable that will make the denominator equal to 0. And we have done a little bit of this last unit because we created new functions by doing division of two functions. And then we said that to find the domain of those functions, we have to make sure we take away those values that will make the denominator equal to 0. It's the same idea, obviously, because it's still a ratio in this situation. So let's practice a little bit with these, with NPVs. X plus 1 divided by x minus 3. All we focus on is the denominator, so x minus 3, and we want to say that the x minus 3 cannot be 0. And then you just solve it like an equation. This one became a linear equation because the expression is a linear expression, so x cannot be 3, and that's our NPV. So it can be any number except for 3. Make sense? 5x squared over x cubed. So the NPV comes from x cubed. X cubed cannot be 0. To cancel the cube, I would have to take cube root of both sides. That will give you an x equal to 0. Cross it over just to show that it's an NPV. You don't have to show all this work when you are finding your own NPVs for any kind of expression of a similar form, like x cubed, x squared, x to the fourth. Obviously, it's going to be x cannot be 0. Okay, but that's how you would solve it to show the opposite operation you will have to apply to it. So you cancel it to a simple x there. The next one, x squared plus 4, the NPV from the denominator. Now let's think about it. Can I plug in here into the x? Think about the x being under the squaring. That's where you're going to plug something in, a number. Can you plug any number in there in such a way that whatever you evaluate as x squared, it's going to give you a -4, because that's the only way you would cancel it to make it 0. Can you get a -4 out of that expression? No, because the only way that you could probably think it could happen is if you put -2 there. But when you square the -2, it becomes +4, right? So you don't have an NPV in this situation. This is just the analytical thinking of not having an NPV. The algebraic showing that you don't have an NPV is solving this equation algebraically. So we would move the 4 on the other side. So it becomes x squared cannot equal -4. So now when you take the square root of both sides, you will notice here you have to evaluate it by taking the square root of a negative number, which is not possible, right? So therefore, there's going to be no NPV. The x's that I'm allowed to have in this expressions are all kinds of numbers. There's no exceptions. You can say x belongs to R if you want to be fancy, right? Just like a domain or a range notation. The last one is x plus 2y over 5x plus 10. This is the rational expression that involves 2 variables. We're not going to deal with these kinds, but I thought I gave you an example just to know that they exist, not the only ones that we talk about, which is only x is in the variable. We're still going to have to focus on the denominator. So 5x plus 10, man, it's like they're moving mountains down there. So 5x plus 10 cannot be 0. Move the 10 on the other side. 5x cannot be -10. Divide both sides by 5. X cannot be -2. Simplifying rational expressions sometimes is needed, especially when we get to functions. We do have to look at the simplified form of whatever expression the function equation takes. So for that reason, we will review a little bit. Some of these are more complicated than the later on, but I feel like with my experience teaching adult ed, a lot of students need more practice with algebra. And if there's anything you will take from these classes into university classes, it is a stronghold of algebra rules and applications. Those are your basics, and then whatever they throw at you with new ideas. If you have a good basics of algebra, you have a better chance of doing well in those classes. So let's simplify 5x squared times y to the 4 divided by x cubed. These are monomials, so monomial divided by a monomial. So all we have to do is apply the quotient law for those powers. So I don't have a number to cancel the 5 with, so 5 it will stay. But then the x powers, we can cancel them, right? The one at the bottom is a little higher than the one at the top. So I would do the reduction at the top, it will cancel entirely. And at the bottom, you can think of it as x to the power of 3 minus 2, which is just 1, right? So we would have 5 at the top so far, and an x at the bottom so far. Okay, so this 2 with this 3 cancel by doing subtraction. So 3 minus 2 at the bottom. And then y to the 4 doesn't have a partner to do a simplification with, so it just stays what it is. Okay. Now, NPVs will always come from the original expression. So even though you are simplifying and you might feel like some of them have gone because you canceled them, the NPVs have to exist because originally that's the expression you're talking about. Just because you can write it in a simpler form, it doesn't mean the NPVs are gone as well. So here we have x to the 3, I think it was. It doesn't matter, x the same thing. Both of these will give you x cannot be 0, right? If you feel like you're gonna forget about the NPVs, you can always state them before you start your cancellations. That might take care of it. But in the end, it doesn't matter when you state them, as long as you remember it comes from the original expression. Original equation, if you talk about function, original equation, if you're talking about finding NPVs for equations. So always the original one. X squared minus x at the top, x squared plus x minus 2 at the bottom. Now here we have a binomial divided by a quadratic trinomial. We can't see if anything cancels unless we have them in factored form, right? Remember, we cannot cross unless we have multiplication. So the first thing we're gonna do is write the factor form of each of these expressions. So x squared minus x, a common factor is x. We're left with x minus 1 in the bracket. That's our numerator in factored form. And then in the denominator, we have a trinomial. What's 2 numbers multiplied? Give me -2 and added, give me +1. -2 and +1, but that's going to give me -1 if I add them. +2, -1, right? Because this gives you back your -2. Those are the factors of -2. Now you check to see if they're in the right factor pair. 2 plus -1 is +1. So all you got to do is put them here. And that's the simplest way of factoring quadratic trinomial. And it only works if right here in front of the x squared you have 1, okay? When it's different than 1, you can't use this method. Okay, it has to be the longer one called the grouping method. And I've seen that in your first test. Okay, we have to revise a little bit the factoring of quadratic trinomials. Okay, now NPVs are easy to be seen right now before we cancel everything, because we can look at the factor form and we can see what x cannot be to make that equal to 0. So in the first bracket, x cannot be. Well, the whole thing cannot be 0. So if I take the first bracket, x plus 2 cannot be 0. What does x cannot be? -2, okay. And then the second bracket, x minus 1 cannot be 0. So x cannot be 1. Okay, so these two are our NPVs. Now we can proceed with canceling, okay. I have an x minus 1 bracket and an x minus 1 bracket. These are factors, so they're multiplied. I'm allowed to cancel the entire bracket. And we are left with x at the top, x plus 2 at the bottom. Okay, now the biggest error that happens is now students want to cancel the x's again. It cannot happen because this you have an x times 1, and here is x plus 2. I can't factor out an x out of these two, right? So if you do the x and the x, it's an error of canceling. Okay, and everything gets thrown out the window because of that cancellation, you're not going to follow through with the right work just because of that, a little tiny error you're making. So remember, you can only cancel top bottom if you can make it in factored form. So a multiplication of some sort, a chunk times a chunk. Okay, it doesn't matter how the chunk looks like, a monomial, a binomial, but it's a multiplication, our factors. Okay, so the next one, x squared minus 5x plus 6 divided by x squared minus 9. So again, we can simplify only if we have them in factored form. So at the top, we have the trinomial this time, also the simple kind, because in front of x squared, you have 1. So we can go ahead and write like this, hoping that we can factor. I think if I remember correctly, we can factor this one too. So let's check. 2 factors of 6 that add up to -5. 6 and -1. If you multiply them, you get -6. So not the right pair. -2, -3. If you multiply them, we get +6. If we add them, we get -5. So that's the right pair. Okay, so you can't make an error with these ones. You can definitely go trial and error until you find the right pair. There's only one pair that works if your polynomial is factorable. So -2, -3. And at the bottom, x squared minus 9. This is the shortcut of the factorization of that. It's called the difference of squared factorization. It's going to be x in each, and then one of these values here is going to be the square root of 9 but positive, and the other one will be the square root of 9 but negative. Okay, so imagine this being x squared minus 3 squared. That's why it's called the difference of squares, because each of those parts are squares. Okay, and then in the first one you put x minus 3, and in the second one you put x plus 3. You can also think about where this formula came about by thinking of this quadratic as this form. And you can ask yourself again, what two numbers multiply give you -9? That when you add them gives you +0, right? So -3 and 3, and then you can go straight there. Make sense? But it has been used so much, but it has its own formula. It's called difference of squares, and you have it here if you want to memorize it. It's useful in the future as well. Okay, and it's also useful in case you don't work with the difference of square where you have a trinomial quadratic, because then you can apply this one. But if you have something like x to the 4 minus 16, then you have to know it's x squared minus 4, x squared plus 4. So this formula works for other situations as well. Okay. NPVs. We cannot have x to be positive or -3. And then we can cancel to finalize our simplifying the x minus 3 bracket. And we're left with x minus 2 over x plus 3. Well, here's an interesting one. Love this example because you can see how useful some of these tricks we have learned are in some situations. So my goal here is to simplify this expression. And I'm going to follow the steps. Okay, I have to factorize if there is any factorization available there. At the top, I'm not seeing it quite yet. But at the bottom, I can see the difference of squares, right? I have the a that's squared, and I have the 4 that's squared to see that 16, right? So that's a difference of squares. And I know how to factorize that. A in each, just like the x's from before, and then I have a -4 and a +4. Yeah. And then I'm looking at this 4 minus a and a minus 4. They're so similar, right? There's a positioner backwards. And the way you can switch the position of either of them, so now they match in terms of the factor, is factoring out a -1 from either of them. I'm going to do it at the top because it's a little bit cleaner. So I make a -1 as a common factor from those two. And then -a divided by -1 is going to be a. I'm going to put the a in the first position. And then 4 divided by -1 is -4. So a minus 4, a plus 4. I'll let you think about that one for a little second here and there, so you can see if it makes sense. I skipped a step in a way. I've done a step in my head, because when you factor out the -1 from here, you would end up with -4 plus a if you just take them in that order. But then I just switch them over so they match. Make sense? Okay, so now I have a minus 4, a minus 4. I can cancel these. And I'm going to be left with -1 at the top and a plus 4 at the bottom. NPVs are from here, so a cannot be. The -1 from here, I factor it out from there. So if you multiply -1 times a, you get this -a, -1 times -4, you get this +4. So we haven't changed the expression itself, just the form of it. It's still the same thing. Okay, and then we had to do that so we can simplify it a bit further. A cannot be positive -4. The last one, I think it's a similar one. B squared minus 6b plus 9 over 9 minus b squared. We can replace these with the x's if you think that's easier. Doesn't matter really what the variable is. So now 2 factors of +9 that added give us -6. -3 and -3. So we have x minus 3. You can put a square, or you can just do it again, x minus 3, like that. And then again at the bottom, you have a difference of squares, because you have 3 squared minus x squared, right? So that leads to 3 minus x, 3 plus x, and that. And now you have a similar situation like before with the a's. You have x minus 3 and 3 minus x. Okay, if you want to be able to cancel that, you have to remember the -1 has to be factored out. It doesn't matter which one, okay? Do you want the top one or the bottom one? It doesn't matter, okay? So which one do you want to factor out? The top, a -1, or the bottom, a -1? Which one? The bottom, okay. So if I put the -1 there in front, extracting it from here, what am I left with in the brackets? X minus 3, X minus 3. Or if you want, first -3 plus X, right, like that. But then why would you write it like this? Because you want it in the other way anyway, right? So you just flip it in your mind. So it's already written in this order. But that's what it is if you go it in steps. This would be step 1 and that would be step 2. And at the top we have X minus 3 times itself. And now we can cancel the X minus 3. And we're left with X minus 3, -1 times 3 plus X. And I'm going to open up the bracket now. X minus 3 over -X, -3. That's one form. If you move the -1 at the top, then you would have 3 minus X. So if you write it as -1, X minus 3 over 3 plus X, it will be a little bit nicer looking. 3 minus X over 3 plus X. They're exactly the same thing. Same expressions. Now, what are the NPVs for this one?
X cannot equal.
That's right. Through all of these operations, they've been multiplying rational expressions. Do the following operations and then give your answer in simplified form. So we have X over 3 times 3X over 4. There's all monomials throughout and some constants. So the first step there, factoring, is not going to apply. We don't have any x's or variables in the denominator, so there's going to be no NPV. And then to simplify, we have to see if any numbers simplify, any variable powers simplify. So in this case, only the 3 and the 3 will cancel out. And you have then x times x, which is x squared over 4. B, x minus 1 over 8 times 4 over x minus 1. Already they're factored, so nothing to do. And then for the NPVs, you only have one expression involving x in the second fraction. So we can see the NPV from there would be x cannot be 1. And then the 4 and the 8 cancel by a factor of 4, right? So 4 divided by 4 is 1, and 8 divided by 4 is 2 there. The x minus 1 entirely cancels with the x minus 1. And if you are stating the NPV, that's okay. All we have is 1 over 2. as our final answer. So if you have an expression that looks like this, I have 1/2 with the condition that x cannot be 1, okay? That's actually a rational expression because it came from this situation, okay? It's not just a number. Okay? And for functions, it will member. And the last one, a multiplication of more complicated looking rational expressions that involve some quadratics. So every single one of these ones have to be factored in a factor form, and then we can see if we can simplify it, and we can also look for NPVs a little bit later on. So let's start with the first fraction. So quadratic trinomial, two factors of -8 that add up to 2. Four and -2. So +4, -2. Denominator, it's a binomial, so we can see x appears in both. So x out, and we're left with x plus 3. Second fraction, difference of squares at the top, x squared minus 9. So the factorized form would be x minus 3, x plus 3. And then x plus 4 cannot be factored further. It's a linear binomial, so that's all done. Before you start canceling it, if you don't want to forget every single one of your NPVs from the denominator, just take them one by one. So from the first here, the first factor, x cannot be 0. The second one, x cannot be -3, and then x cannot be -4 from the last fraction. Which one? Which one? The zeros from here, because this is part of the expression. One, well, no, because 1 is not gonna make it 0, right? So when you're equalizing this x plus 3 equals 0, the way this expression can be 0 is if this is 0 or if that's 0. So when we're saying split and solve, that's what we mean. What's gonna make it possible for this to be 0? You can multiply by 0 either by having this x to 0, the 0 times whatever you have here, it doesn't really matter anymore, because it's gonna make it 0, right? And then forget about this one now and say, okay, now this is 0, then I don't care what this one is, because it's gonna make it 0 anyway. 0 times something is gonna be 0, right? So now each part, you make the condition to be 0. X cannot be 0, or think about it like this. X plus 0, x plus 3. Right? If you want it like as a binomial, because it makes a little bit more sense, because we have seen so many binomials up to now, right? All good? And then canceling out. So let's see, x plus 3 from here with the x plus 3 from there. X plus 4 from here, x plus 4 from there. And we have at the top x minus 2 times x minus 3. And at the bottom, x. Now let's get rid of the bracket. X squared. At the end, you have 6. And in the middle, you have -5x over x. How are you doing? Hanging in there? Okay, so now dividing is around one, I think, before we do, no, adding and subtracting, okay, dividing rational expression. 5a to the 4 divided by -2, then divided by another fraction, 5a, everything squared. Dividing rational expressions are a bit more difficult because we don't have a rule to divide them directly. We have to go through multiplications of fractions. So the rule is you keep the first fraction exactly as it is. And then you times it by the reciprocal of the second one. So the second one flips over upside down. That's what we say reciprocal. 1 over that will make it upside down. Now what happens here when you apply the rule, okay, even though from the initial situation, you don't have an NPVs, when you go through this flip over, you create a new fraction. Well, that fraction has to exist at this point in time. So you gotta make sure you talk about the NPVs that appear along the way as well. So state the NPVs for both and along the way. Once you do this flip over, if they appear. So in our situation, the NPV, once we flipped over, it's from here, from 5a, a cannot be 0. Now let's go ahead and see what we can do here. I can definitely deal with the 6 and the -2 if I want at this point in time. Or I can deal with the power of a product first, meaning like getting rid of this bracket, okay, to apply the square both to 5 and to a, and do all of the simplification all at once, okay? So it's really up to you. It's part of your personal style. I will do that. Multiplications, divisions. I lost track of my colors here. So 5 square is 25, a square is a square. So now I'm going to simplify. 6 with -2, I can divide by 2, both of them. So -1 and 3. 5 and 25 divided by 5. So 1 and 5. And A4 and A2, the higher one is at the top, so the subtraction will happen at the top, and the answer will stay at the top. So a to the power of 4 minus 2, which is going to be 2, right? So basically, this is gone entirely, and from here, you're only going to be left with 2. What are we left with? We have a squared times 3 over -1 times 5. Now let's rewrite it nicer. 3a squared over -5 or -3 over 5 times a squared. There's a lot of different versions again of the same thing. I need a break. Do you? I need a break. Okay, let's take a break and we'll. Okay, so division of fractions rule is again keeping the first fraction the way it is and the other one. And then the reciprocal of the second one. So x squared minus 3x minus 4 over x squared minus 7x plus 12 times 2x minus 6 over x squared minus 1. Okay, let's take them one by one and factor them. 2 factors of -4 that add up to -3. -4 and 1, right? So -4 and +1. And 2 factors of +12 that add up to -7. -3, -4. A 2 from 2x minus 6. Then we get x minus 3 in the bracket. And x squared minus 1 is a difference of squares again, because 1 can be written as 1 squared. So remember that formula. X in each, and then -1 plus 1 for the difference of squares. Okay, now let's tackle the NPVs. So first, we would have had NPVs from this. So that's the expression that we factored from there. And then from here, okay, which ended up over there, right? And then after we flip it, we also ended up with an expression that contained x in this fraction, which is that one. So you have a bunch of NPVs from 3 spots now because of that reciprocal. So NPVs, we have a 3, a 4, and positive -1, right? Make sense? So it cannot be positive -1, cannot be 3, cannot be 4. Let's cancel now. X minus 4 with x minus 4 is gone. X minus 3 with x minus 3 gone. X plus 1 with x plus 1 gone. That cleans up quite nicely to only a number 2 at the top and x minus 1 at the bottom. And last one, it's still division, but written in stacked form. So find the middle of the expression. That's going to be where your division line is, okay? So that's divide. This is your first fraction divided by the second fraction there. So let's rewrite it in a form that is easier or similar to the ones we have done so far. So it would be x squared over x minus 1 divided by x plus 2 over x squared minus 1. So these two forms are the same thing, it is written differently. Okay, so apply the multiplication rule times reciprocal of the second. So x squared minus 1 at the top, x plus 2 at the bottom. Now let's factor. X squared I can't factor. X minus 1 I can't factor. X squared minus 1 again, difference of squares. Minus 1 plus 1. And x plus 2, I can't factor further. Now let's look for MPVs, see where they come from. This is my original division, so I should have an MPV from here, which is that one. NPVs from there, which is that one. Then after I flipped it over the second fraction, I also should have an NPV from that. So x plus 2. You can see the pattern, right? That you have to take the NPV from both top and bottom of the second fraction. Okay. Canceling. We have x squared, x plus 1, and then x plus 2 at the bottom. Getting rid of the brackets because we don't need them anymore. X cubed plus x squared over x plus 2 with the MPVs. X cannot be positive, -1 and -2. Before you panic, I'm not gonna ask you questions like this in the test, okay? Remember, I'm doing this for you, for your future. Okay, just to see that, again, to remind you that algebra is important for later on. You'll see the types of questions we will do when we get to equations, okay? Adding, subtracting rational expressions is the last one before the equations. How are we doing? Okay. So when we add, subtract fractions, we have to make them the same denominator. With expressions, now you have to be careful because your factor forms is going to show you what is going to be the lowest common multiples of those expressions. And again, the factor forms come from polynomials, so you have to have your polynomials in factor form so you can see again the lowest common multiple. It's not as easy as it is just for numbers, okay? So in the first situation, we have 7x and 2x. These ones are easy to do because the x appears in both of those denominators, right? So the common x is going to be x, right? The lowest common multiple for x terms. Between 7 and 2, you need the lowest common multiple between 7 and 2, which is 14, right? So 14 and then x. That's the lowest common multiple for both of those expressions. And now here you have to see the change that happened from 7x to 14x. You times it by 2, so you have to times by 2 at the top as well. I like to write it like that. And then 2 times 3y is 6y. And from 2x to 14x in the second fraction, we multiplied by 7, so I would have to times by 7 at the top as well. 7 times 5 is 35y. Now that you have two fractions with the same denominator, you can keep the denominator. So you just write it once. And add the numerator, 6y plus 35y. And if you have any like terms, you put them together. 6y plus 35y is 41y over 14x. NPV always for rational expressions from 7x and 2x, both of them are just with x's in them, so x cannot be 0. Now, I like to do my work when I show addition or subtraction of fractions. From here, I skip straight there. So I find the common denominator, and then I just say times 2, and I go straight to 6y times 7, go straight to 35y. So for me, the step is extra. So I often don't show it, okay? But if you like to show that intermediate step, go for it, okay? If it makes sense to you. Okay, in part B and C and D, I will probably go straight to the second step here. So if it doesn't make sense, let me know. So what I want is common denominator, bless you. And again, remember, I'm going to skip to this step. So that's why I have only one fraction, because I will do it all at once. So between 3 and 5, the lowest common multiple is 15. You want a multiple that divides both 3 and 5, right? And then between x and x squared, you want the higher of the power, because you want that power to divide both of them. Okay, so never the lower one, you want the higher one. So x squared. So 15x squared is our common denominator. And now I look at individual fractions again. From 3 to 15 is times by 5. From x to x squared is times by x, right? So I have to times by 5x at the top there. So 2 times 5x is 10x. That's my first fraction, basically, right? And now we're going into the second one. From 5x squared to 15x squared is times by 3. So I times by 3 at the top too. And then I do the multiplication at the top. 3 times -1 is -3. And that's basically your second fraction. Now, can we do anything further? No, right? Everything is done. I can't factor an x to simplify with the x squared, so it's pretty much it. All we is left to do to not forget the NPV here for this one as well. X squared, both of them would give x cannot be 0.
Got 5x, times 5.
Because from 3x to 15x squared, our lowest common multiple, you have to times it by 5 to get the 15 and by x to get to x squared. So 5x. So when I do 5x times 3x, that's how I'm getting the 15x squared. Right, so then I have to apply the same multiplier to the top as well. This fraction is the equivalent fraction of the 2 over 3x. So if I simplify the 10 and the 15 by 5, right, I get 2 and 3. The x and the x squared, I get 1 and x. So I'm getting back my first fraction. Right. Clear, everyone? Thank you, Luke, for that. Good job. All good? Okay, let's go to the next one. Now we're having some binomials in the denominator. Every time you have an expression that's in factor form and you cannot factor it further, think of it as being a prime, okay? So when you finding the lowest common multiple of primes, all you gotta do is multiply them. That's gonna be your lowest common multiple. For example, when we added 1 over 2 with 1 over 3, the lowest common multiple between 2 and 3 is 6, because number 2 is a prime number, number 3 is a prime number. All you do is times them. Okay? Now, when you have, for example, 1 over 2 plus 1 over 6, okay, what's going to be the lowest common multiple this time? It's 6, right? It's not 2 times 6, because that's not the lowest. It's still a multiple, but then you're going to go too high. So in that case, you think of 6, you not really think of 6, but you can think of 6 as 2 times 3. And basically, you only take the ones that are primes, right? So 2 and 3, 2 being the common over there. I only need to take the 2 ones from each of those fractions. The same thing is going to apply for prime or non-factorable polynomials, in our case, x plus 3 and x minus 2. The common denominator is going to be x plus 3 times x minus 2, just like this one, okay? Multiplication. I think this one I'm going to do it in 2 separate fractions because it's going to be difficult otherwise. So minus, again, second fraction is x plus 3, x minus 2. So that's our first fraction, that's our second fraction. Now, in the first fraction, I didn't have x minus 2 as a factor, right? We just times it there to make it an equivalent fraction. So that means I would have to multiply by x minus 2 at the top as well. So we're going to be having 4 times x minus 2. Notice how if we cancel x minus 2, we're going to get back the 4 over x minus 3, right? It's just an equivalent fraction. Clear? Now, in the second one, I used to have x minus 2, but now I'm multiplying by x minus 3. So the x minus 3 is going to be multiplied at the top. So minus 5 times x minus 3. Is it plus 3? Plus 3. Yeah. Okay, so those are the 2 separate fractions. I usually skip this step again, but I wanted to show you in detail how you get those answers. So now when we subtract, add, we keep the same denominator. So that means we just write it once. So x minus plus 3, x minus 2, that's our common denominator. We write it once. And at the top, we just subtract or add our numerators. 4x minus 2 minus 5, x plus 3. So can you see how you can skip this second step here? Just find the common denominator and then think, okay, what do I have to multiply at the top? There it is. What do I have to multiply at the top? There it is, right? You don't have to do all that writing all the time. Now let's continue on over here. So at the top, we can open up those brackets, and if we have any like terms, we will simplify. So 4x minus 8 minus 5x minus 15. At the bottom, again, we open up that. We have x squared plus x minus 6. Yeah. Like terms. Like terms. So at the top numerator, we have negative x and negative 23, x squared plus x minus 6 in the denominator. NPVs from here, x cannot be negative 3 and 2.
Square 4 or plus
Plus x. We're skipping D. We're going straight into equations. If you want, you can do D. I'm still put it in the video in case you're gonna check your work. The D. You apply the same approach and you'll get the answer. So let's go into what we are interested in, which is solving rational equations. Now, a little bit of background, just to then clarify what these directions mean. So you're not getting confused when you have to write your answers to some questions in tests. When you see the word solve, okay, that means you're looking for a possible X that will make the equality true, okay? So you want to find a number, a solution to that equality, okay? So it's not simplifying, it's not calculating, it's actually solving, okay? Now, rational equations cannot be solved in their own special way, like quadratic equations. You can do factoring or square rooting, okay, or linear equations. They actually will become these types of equations as you go along to simplify them in that way. Now, in the process, once you get to a quadratic or once you get to a linear equation, you're going to have to apply those rules to solve those equations, right? And you will get the solutions to those equations, but they might not necessarily be all of them the solution to the original rational equation, because the rational equations have non-permissible values. For that reason, you always want to make sure before you start or at any point in time, go back to the original equation and rethink your NPVs, okay? What part in the original equation I cannot have from the denominator that's going to make it equal to 0? Those numbers cannot be the solutions to your rational equations. Okay, so NPVs become really important now to be stated. At any point in time, it doesn't matter to me, but on your page somewhere, you have to have the NPVs, okay? So I will do them at the beginning. I have just an expression here as x minus 4. You can think about it as being over 1, just like any number you can write as a fraction by putting it over 1. So we notice that we only have an x right there in the denominator in the second fraction. So that means our NPV is or cannot be 0. X cannot be 0. All right, so now my favorite approach to solve rational equations is to make them an equality of two fractions, of two rational expressions. So something like this. But it has to be in this form. A fraction equals another fraction, not like that, right? This is two fractions added equals a number, okay? That's not what I mean. I want exactly that, okay? And then once you get to this form is called a proportion, okay? And then you can just cross multiply and make a new equality. A proportion has that property. So 1/2 equals 2/4. Now, if you multiply these numbers and those numbers, you get another true equality, right? 1 times 4 is 4, 2 times 2 is also 4, right? That's a property of proportions. That's my favorite way to deal with these ones. Now, this is sort of a shortcut if you want, as multiplying both sides by x here to cancel out the x, you're still going to end up in the similar position. So feel free to use any kind of algebraic rules that you know how to use, okay? As long as you know and you have a good hold on them and you're not making errors along the way, okay? So here I have over 1, I made it into a fraction. Here I already have a fraction of -1/x. Since the proportion, I can cross multiply at this step. What am I getting when I cross multiply? I will get x times x minus 4 equals 1 times -1. I'm doing it really slowly. I would definitely skip some steps here. if I were to do this work by myself. But I want you to see where the cross multiplication comes from and how it looks like when you create this new equality. Okay, so now we're gonna multiply through to get rid of the brackets. X squared minus 4x equals -1. Now, what kind of equation did this one become? So we started with the what we call rational equation, and it became a quadratic, right? It is algebraic, yes. They are all algebraic equations, yes. They're the same category, umbrella of algebraic equations, but it's the type that we learn it's called quadratic equation because the highest x term has the power of 2, right? So I would move the -1 on the left, make it equal to 0. And then I would go to the motions. I would try to factor it first. So what's two numbers added together will give me -4 multiplied, give me 1. Is there such possibility? No, there isn't. So I can solve it by factoring. It doesn't mean you cannot solve the equation, okay? It just means that you cannot solve it by that method. So usually when I pass the factorizing method, I go straight to the quadratic formula. So A is 1, B is -4, C is 1, and just apply the quadratic formula to it. So X equals -B plus minus square root of B squared minus 4 times A times C, everything divided by 2A. This formula is in your formula sheet at the very top, if I remember, top left corner. So it's -B plus minus square root of B squared minus 4AC divided by 2A. Okay, so just plug it in, and now you just have to simplify it, okay, and see whatever expressions you get. A lot of the times, it's very likely you're gonna get an expression that becomes something with a root in it. That's okay, just leave it alone, don't evaluate it, because you sometimes are asked to find exact values for your solutions. That means not simplify, what's the word I'm looking for? Estimated. So you don't want to estimate it to whatever's closest or to a nearest 10th or 100th. You want to leave it in its exact form, okay? So let's simplify. I'm running out of space, so that means I'm going to write one of these solutions a little bit below. So I would have a 4 there from negative and a negative, plus minus square root of 16 minus 4 over 2. X equals 4 plus minus square root of 12 over 2. This one can be simplified further. 4 plus minus, because square root of 12 is actually 4 times 3. And I can extract root 4 from under the square root there of square root of 12. So you're going to end up with 4 plus minus 2 square root of 3. Now we can factor a 2 between these two terms. And the 2 will cancel out now with the bottom 2. So X will be 2 plus minus square root of 3. Or one X is 2 plus square root of 3, the other X is 2 minus square root of 3. We just put them together. Less writing to do. Then once you get your final answer, you look at your NPV and you make sure that it doesn't have exactly the same answer. Okay, you always have to cross-check it. It's not the same thing as 0, right? So we can keep the new solution, which is the solution of the quadratic. But once I check the NPV, it's also the solution to my original rational equation. Okay, we started in fourth with the harder one that had a quadratic formula. Let's do one more, or 2 or 3, as many as we can until 4:45. So, B. It's already in a fraction equals a fraction, agreed, right? So we can cross multiply. And we're gonna have x plus 1 times x minus 2 equals x minus 1 times x plus 2. Let's state the NPVs. X cannot be 1 and 2 from the denominator. And we can now get started. We're gonna get one quadratic on the left and one quadratic on the right. So x squared minus x minus 2 and x squared minus x minus 2 on the right. Plus x, right, for this one, plus x. So x squared minus x minus 2, x squared plus x minus 2. Now we can move everything on the left and see which terms will be like terms to cancel out or put them together. So we have x squared minus x minus 2 minus x squared minus x plus 2 equals 0. X squared minus x squared gone. Negative 2 plus 2 gone. So we have negative 2x equals 0. X equals what? 0. Make sure you double check with your NPVs. None of our NPVs were 0. So that's the solution of our rational equation. Now, by the way, how do you check solutions to equations? Who remembers? So this one is just testing it to make sure that it's not one of the NPVs, okay? Because sometimes it may become, because we're solving other types of equations. But now that I got and I say, okay, I think this is going to be my solution. How do I check it? You just plug it into the original equations, keeping the left-hand side and the right-hand side separate, calculate what you're getting, and you want to make sure that your left-hand side equals the right-hand side. If it does, your solution is correct. If it doesn't, then it's incorrect, right? So here, if I have 0, I will end up with negative 1 on the left, and 2 divided by negative 2, also negative 1 on the right, okay? So that's how you check. Let's do C. Now, if I were to apply my approach for C, since it's an addition over there, I would have to first go through the operations that I'm seeing, addition, multiplication, whatever the operation is, to merge it together into one single fraction, okay? We already have done that skill today. We said if I want to add fractions, I have to bring them the same denominator, right? So let's find the common denominator between x and 2x. 2x. And then here, I didn't have 2 in the denominator, so I will have to multiply by 2 in the numerator. So it will become 4. The 2x was there in the second fraction, so I don't have to multiply by anything. So plus 1. Any number can be written as a fraction by doing over 1. So there's your proportion, right? Fraction equals a fraction. We can take it one more step. 5 over 2x equals 10 over 1. Cross multiplying. 2x times 10 is 20x. 5 times 1 is 5. Divided by 20 both sides. X equals 5 over 20. Or in the simplified version, 1 over 4. 1/4, right? NPV, let's see if we keep that. NPV for the original one is x cannot be 0. One over 4 is not 0, so this is a solution to our rational equation as well. D. Two x minus 1 over, at the denominator, we have difference of squares. We've seen it so far when we simplified our rational expression. We want to open that up into a factored form into x minus 1, x plus 1 equals 1. I can write 1 as a fraction as 1 over 1. NPVs from here. X cannot be positive or negative 1. And let's proceed. You can definitely cancel out the x minus 1 at this point. And we're going to be having 2 over x plus 1 equals 1 over 1. Cross multiplying. X plus 1 times 1 equals 2 times 1. X plus 1 equals 2. X equals 2 minus 1, which is 1. Now, this is a solution to this equation, to x plus 1 equals 2, because that's what our rational equation became, right? But it's not the solution to the original rational equation, because I cannot have x equals to 1. If I plug that in, I'm going to end up dividing by 0. Not possible, okay? So not solution, that means no solution for this situation. Sometimes when you're solving quadratic equations, you're going to get 2 solutions. And sometimes one of those solutions is not a solution to your original rational equation because of the NPVs clash. So don't forget about NPV, always check. And the NPVs check is basically a shortcut for you plugging in and comparing always the left-hand side with the right-hand side, right? So kind of like having the confidence I am getting the right answers here, all I have to do is make sure they're not the NPVs, okay? Now, I'm not gonna lie to you, this is difficult. You know, there's a lot of different kinds of rational equations out there, and you need to do a lot of practice questions. You do have some practice questions in the your turns. You have some practice questions in your worksheet number 1. And I have an extra practice question sheet that I can post on online, and I can also photocopy it for you as well before you go home. So all I can say is practice, practice, practice. When you felt like I've practiced enough, practice again. Okay?